In today's lecture, we are going to discuss how to design a full adder circuit using PAL. In the previous sessions, we have discussed how to design half adder using PLA, and we have discussed the difference between PLA and PAL. In the case of PLA, both and OR are programmable. PLA and PAL are two types of PLDs. In PLA, both and OR are programmable. In the case of PAL, only the AND is programmable and OR is fixed. We are going to see how to design it. The first step is to draw the truth table of full adder. So already we know this. We have designed this using normal Boolean functions. If it is a full adder, we will be having three different inputs and two outputs. So since we have three different inputs, we will be having 0 to 7 combinations, 0 binary representations of 0, 1, 2, 3, 4, 5, 6 and 7. This is the binary representation for the inputs, and the sum and carry will be 0, 0 here. Here it will be 1 and 0. Here again 1 sum and carry. So when we add 1 and 1, the sum will be 0 and carry will be 1. Here we have. This is the truth table for full adder. If we want to design a full adder, we know that we have three inputs, right? A, B and C are the three inputs. So since we have three inputs, we will be having 8 different combinations that varies from 0 to 7, right? So 0, 0, 0 to 7. Here the relevant sum and carry. When we add 0 with 1, we will get 1 and carry. If it is 2 ones, then the sum will be 0 and carry will be 1. If it is 3 ones, both sum and carry will be 1. Already we know the binary addition. Now in order to design a digital circuit, we need a Boolean expression, and so using a K-map, we are going to find the Boolean expression. Here we have two different outputs, and for the two different outputs, we are going to find the Boolean expression using K-map. Since it is a 3-variable structure, we will be drawing a 8 cell, 2 or 3 cell K-map. So A, B, 0 and 1, 0, 0, 0, 1, 1, 1 and 1, 0. From the sum, it is 0, 1, 1 and 0. Then again 1, 0, 0 and 1. So for the sum, this is the K-map. And now we have to group the K-map and we have to find the expression for sum, right? So from this, we know for this grouping, it is A dash, B dash, C. Plus for this grouping, it is A, B dash, C. All these are basics. And for this group, it is A, B, C. Plus for this group, it is A dash, B, C dash. This is the expression for sum, and similarly we have to find the expression for carry. Again for carry, we will be drawing an 8 cell K-map, right? A, B and C, 0, 1, 0, 0, 1, 0, 1, 1 and 0, 1. This is 0, 1, 1, 1 and 1, 0, right? So here for the carry, it is 0, 0, 0, 0, 0 and 1. Then again, here the carry is right. Carry is right. Okay. So again, for the fourth case, 0, 1, 1 and 1. This is how the carry for K-map. The K-map for carry looks, and we know the conditions for grouping, right? Applying all the conditions for grouping, we can find the expression for carry, right? For this group, for the group which I have marked in blue color, the value will be B, C. Plus for this, the common term is A here in the row and C here in this row. Plus for this, it is A and B. So we have found the expressions. For the sum, we have found an expression. Similarly, for the carry, we have found an expression. Now we have to draw the structure for PAL. There is a small difference between PAL and PLA. That is, in the case of PLA, the AND is also programmable. Here, the AND is programmable. The OR is So first we have 3 inputs. So let us consider all the 3 inputs A, B and C, and also we have inverted versions. So using an inverter, let us consider A dash. So I am considering this as A, B, C, and so this will be A dash, B dash and C dash. Now, how many number of AND gates? In the case of PLA, the number of AND gates will be equal to the number of minterms, right? Here it is not so. Here the number of AND gates will be, see, this sum has 4 minterms and this carry has only 3 minterms. So the maximum number of minterms will be the number of AND gate for every single output. We have 2 outputs, sum and carry. For sum, we will be having 4 AND gates because the logic is 0, and for carry, we have 4 outputs. So 4 different AND gates will be drawn, right? And finally, we know that we have 2 outputs. Similarly, we will be having 2 outputs as already we know, right? The 2 outputs are for sum and OR gate and for carry and OR gate. So this is for sum and this is for carry. Now how to draw the fuse diagram? So let me write all the minterms. So this is, let this be the minterm intersection for A dash, B dash, C dash. This is for A, B dash, C. This is for A, B, C, and this is for A dash, B, C dash. And let this be for the carry BC, the first minterm, for the second minterm AC, and the third minterm AB. See, this AND gate we will not be using, but we have to mark it here, right? An AND gate which is not used. And see, the OR gates are fixed, so we will be fixing it. For sum, these are the 4 AND gates which is fixed. We will not fuse it, we will be fixing it. And for the carry, we will be fixing it. Right? If we fuse, we will be marking a cross. Here we don't fuse it. Now we can fuse, and is programmable in the case of PAL. So we can fuse it A dash, B dash and C. Similarly here A, B dash has to be fused and C. Here A, B and C. Here A dash, B, C dash. Here it is DC, B and C. Here it is A and C. Here it is A again and B. Right? So here in the case of PAL, we will be programming AND array, but we will not program OR array. OR is